introduction. So, hello, my name is Luca, and today I'm presenting our work titled Hazard-Driven Threat Modeling for Cyber-Physical Systems. In recent times, attackers aiming to disrupt physical processes that run within cyber-physical systems have shown the ability of infiltrating enterprise networks deployed around CPSs and use systems' own feature to compromise the safety of its functionalities. This is possible because often we miss causality links between the exploitation of vulnerabilities on individual components of the system and emergent properties such as the safety. We also know that safety and security, especially in the field of cyber-physical systems, intersect in complex ways. This leads to scenarios in which an attacker, for instance, could specifically target a device that has been introduced to guarantee safety to compromise its availability and then perhaps compromise the availability of the process itself as a response, alarm response mechanism, or even worse, they could target the integrity of such a safety device, therefore masquerading something to cover something that's going on. And this can lead to catastrophic effects. In this paper, we proposed a methodology to perform a threat modeling of a cyber-physical system, which is driven by hazards. We start by conducting a safety analysis of the system. Therefore, we identify hazards and losses. And then we apply system theoretic process analysis to identify hazardous control actions. Now, for those of you who are not familiar with STPA, with system theoretic process analysis, an hazardous control action is a control action that can drive the system towards an unsafe state if it is applied in specific context. An example of that could be the command of closing a door that can trigger a hazard if it is applied when somebody is passing through the doorstep. Then we start with the actual threat modeling activity. We define potential high-level objectives for the attackers, as well as their capabilities, and we also define scope and modalities of the attack. This latter will help in defining an attack graph to identify possible attack path for the attacker. Then we jump on an architectural representation of the system. We map the high-level objectives the potential high-level objectives that we found onto the architectural components of the system. And we enumerate what we call target nodes, or basically the architectural components of the system on which the attacker will try to acquire privileges in order to have enough privileges to control parts of the information flow in the system. Given the targets node, and assuming that we can compute the attack graph of the system, we now have, we can retrieve attack paths leading to the exploitation of these specific target nodes. So the acquisition of privileges on the information flow. In this work, we use STPA to show that which information flow the attacker needs to interact with in order to cause a catastrophic event. By doing so, we expose the existing causality between the exploitation of vulnerabilities on system components and high-level hazards. And we show that our methodology also offers the tools by means of through a bridge with the behavioral representation of the systems. It also offers the tool to potentially quantify the impact that an attack has on the against the system performances. We also, before going further, I'm going to briefly discuss a short use case that we used in our work to show the application of our methodology. It features a communication-based train control system with N trains running through a rail network. We have a zone supervisor to which each train constantly communicates its own position and speed. Also, each train receives from the zone supervisor is assigned speed limit, depending on the position where it is on the track in that moment. Finally, we also know that each train communicates with the train that precedes its position. This is for the preceding train to be able to keep a safety margin. We identified two possible safety requirements for the system. One is that each train must always keep a safe distance between itself and the train that is running ahead of it. And then also each train must observe the assigned speed limit. So it must never overrun the assigned speed limit. Given a set of losses and hazards, in this slide, we report a subset of hazards for the system, which are collision identified under the AD H1, derailment H2, and disruption of operation H3. The hazards here are listed in order of how heavy the consequences are in terms of losses, both in economics, in terms of economics losses, or in damages to human lives or properties of the company. In this work, in order to take into account multiple aspects of the cyber-physical systems, we perform a combined analysis of different models. We expand the work done by Han et al. And Erickson et al., both published in 2015, and bridge together an architectural and behavioral models of the system with its functional representation. Now, while the architectural model represents those components that deployed together effectively build up the cyber-physical systems, the behavioral model shows how the output of processes and controllers inside the CPS evolve in time. These two models are bridged with the functional representation of the system, which is nothing more than a system-theoretic model, which is made of three elements, which are components, information flows, and subsystems. Among these, perhaps the most important is information flow, since in our threat modeling activity, we discuss the ability of an attacker acquiring privileges on a piece of the information flow. In order to account also for cascading effect of attacks across the system, we define a dependency relationship between data flows in the system. We say that the data flow D2 depends on D1 if D1 is computed using the D2 as using D2. Therefore, if the integrity or the availability of D2 gets compromised, then we're going to have problem on D1, given that there is no mitigation or in between. On the right hand of this slide, you can see an example, the system theoretic representation of the use case, particularized to the case of train I. So we can see that train I exchanges its position and speed with its own supervisor, from which receives the speed limit. And also the train controller computes throttle and brake commands, respectively under the ID of D7 and D8, taking as input the speed limit, the position received by the train that is running ahead of it, the position, and also the position of the speed from the onboard instrumentation. In this table here, we show the first result of the application of STPA, of the system theoretic process analysis, which explain the consequences of the unsafe application of the control actions brake and throttle. So basically, given the system theoretic model, we applied STPA to brake and throttle control action to understand in which unsafe scenario the system can go towards an hazard. We see that if the braking control action is applied when it's not required, then the system will undergo into a hazardous scenario H3, which represents a disruption of operation. Way worse is the case in which the braking action is required and not applied. Then we risk a collision or a derailment, depending on the context in which the braking action was applied in the first instance. And so on. In the table, you can see other the other results of the unsafe application of the two control actions. We now start describing the actual threat modeling activity. As I mentioned before, we start on the assumption that the attacker tries to acquire privileges on the information flow in the system. This threat modeling activity is consists in characterizing the high-level objectives of the attack and the modalities of the attack, These two characterizations are carried out on the system theoretic model of the system, while we also characterize the adversary in terms of resources and capabilities that they have and the scope of the attack, meaning if the attack is a purely cyber attack, is a purely physical attack, or is a cross-domain attack. These last two will help building up the attack graph, starting from the architectural model of the system. We account for two possible high-level objectives to be defined, namely mission disruption and mission hijack. The difference between the two is that in the first case, the attacker will try to trigger an hazardous scenario, while in the second one, the attacker will try to make the system behave as they want to. And high-level objectives requires the attacker to achieve the control of one or more information flow. We recall that a control action is carried out by an information flow. And they can achieve the control of information flow through, they can have an impact on information flow through different modalities. They can directly targeting the information flow transporting the control action, so they can gain enough privileges in the system to effectively compromise the availability or the integrity of the control action itself. They can gain enough privileges to compromise the feedback that is used to compute the control action, and this is an indirect attack through the feedback, or they can perform in a more general way an indirect attack which is on any of the dependencies of the control action in the system. In order to understand better the privileges that the attacker, how the attacker can start from an initial exploitation on the system perimeter, how they can get from the initial exploitation to actually gain enough privileges in the system to on the information flow. First of all, we assume that it's possible to build the attack graph for the CPS. And then we also assume that, we build it by considering the attacker capabilities and resources, and also the scope of the attack. If we also account for cross-domain attacks, such as, for instance, the intentional exposure of a heating sensor to a heat source, then we will have additional nodes representing the action for the attacker. On this slide here, we represented the attack graph for a subset of the onboard instrumentation on the train. The attack graph is represented using the syntax proposed by Schimming et al. In 2005 with Molval. We have three different kind of nodes. We have the squares, which are preconditioned to the exploitation of the attack. We have the circles, which represent the exploitation itself, and then diamonds represent the privileges on the architectural model that the attacker has acquired given after an exploitation. In order for an exploitation node to be executed, all the preconditions must be true. So in this case, for instance, 7, 8, and 9 represent that the attacker has, that there is a database connected to the subnet. The database is vulnerable to a certain vulnerability that goes under the CVE-YYY. And then we have that the attacker is connected on the same network. If these three preconditions are true, then the attacker reach the node 5 of the attack graph, which from the architectural model perspective means that the attacker has now access on the CAN bus, assuming that the database was an historian with a double interface and access to the CAN bus. But also from a functional perspective, this means that the attacker has reading access for the data flows D1 to D8. In this slide here, you can see the existing relation between the attack graph and the dependency model of the information flow, and the dependency between the information flows that we built for the system theoretic model. We can see that the break control action depends on the output of the controller, which itself is computed using speed, position, the speed limit, and the position of the preceding train. Now, the fact that the attacker has reached node 5 means that the attacker has reading privileges on those data flows. We note that the historian has not been considered as a target node. We highlight it in yellow rather than red, mainly because the confidentiality of this information flow was not among the constraints that was considered during the initial phase of the analysis. If telecom information regarding the train position and speeds was a cause of, for instance, economic loss for the company, then the loss of confidentiality of on the data flow, meaning the reading access of the attacker, would have been considered within the high-level objective of the potential high-level objectives of the attack. And then the database would have been highlighted in red in this sense, because the attacker, a potential objective of the attacker could have been reaching the node 5 of the attack graph to expose the information about speed and position. This is not the case. The attacker, however, can use the privileges that is acquired on the architectural model with the exploitation of 6 to pivot in the network. And if 3 and 4 are verified as well, meaning that the controller, for instance, is vulnerable, they can acquire some privileges on the controller that give them privileges, enough privileges on the system theoretic model to write the breaking control action, and therefore potentially cause a hazardous scenario H1, H2, or H3. We ran some simulations in our work to we ran some simulation to correlate the position, the privileges that the attacker gains with the effects that they can have on the system theoretic model, with the effects that they can have on the behavior of the system. And in order to do that, we leverage the bridge that we did with the behavioral model of the system. Now, in this slide, you can see a case in which the attacker is not interfering yet with the system functionalities. On the left, we have the position of the 2 trains running in the infrastructure. The blue line is the preceding train that we call leader, while the red line is the train running behind it, which is a follower. And you can see that the follower always managed to keep a safety distance on the left diagram with the between itself and the leader. Since we have a synchronization, effectively a synchronization in the position, we expect to find a synchronization in velocity as well, which is displayed in the speed profile on the right. This is the first case of mission disruption. In this case, the high-level objective of the attacker is a mission disruption, and they can achieve it through by causing a collision event or a derailment event or a disruption of network operation event. In this case, the attacker is trying to achieving a collision by the unsafe application of the control action break. In this case, the attack directly targets the control action. We have an additional false data injection that is made at time 150. We can easily identify it on the speed profile from the spike on the speed profile. In this case, we have been lucky because the integral action in the controller rejected the injected disturb. This wouldn't have happened if the disturb was not constant. However, even if the train don't really collide to get with each other, we can see that the follower gets drops its distance with the leader. So we can say that the system has become unsafe for some time. This is a second case of mission disruption. And in this case, we can see the attacker achieves a disruption of operation by effectively limiting the speed of the follower. From the first diagram, we can see that the follower is proceeding way slower than the leader. And this is an interesting case because the attacker hasn't been achieved by directly targeting the control action, but rather targeting an information flow which is in a dependency relationship with the control action. Finally, this is the last case, and it's a mission hijack case in which the attacker, rather than targeting one hazardous control action, is trying to acquire privileges to access a subset of information flow. In order to understand which information flow the attacker needs to access and which privileges the attacker needs to have on them, we need to analyze the control structure. In case of a simple control structure, for instance, even an LTI control loop, the attacker may needs to close a loop between itself and between themselves and the process, and gain and control to enough actuator and reading to enough sensors so that the observability controllability matrix has full rank on that. In other case of distributed control systems, like this case, for instance, the attacker may leverage the topology of the network to make the system behave like they want. In this case of mission hijack, the objective of the attacker is to slow down the follower and to increase the distance between the two convoys. And we see that they achieve it from the first graph, in which we see that the distance between the leader and follower has increased. Finally, in this paper, we have shown that the mapping between different views by application of these examples and with this work, we have shown that the mapping between different views of the system can lead to a better, improved safety and security analysis by highlighting potential attack path of interests. We have shown that how an accurate mapping between the functional and architectural model of the system can highlight hidden causalities between the exploitation of vulnerability on system components and high-level hazard. Plus, by bridging the functional model with the behavior representation, we can also understand the impact on the system performances of the attacker's actions. Thank you.